Welcome to today's class. Today we are going to deal about the divergence theorem. Actually, this is going to be the uh, generalization of your Green's theorem. So we are having the Green's theorem as the integral over C of f dot n ds equal to double integral over r divergence of f dA. So the divergence theorem, what it says is that it's going to be the generalization. As I said, it generalizes the result in case of vector fields. So in three-dimensional space. This theorem is also called Gauss theorem. So another name of this theorem is divergence theorem is Gauss theorem. Gauss theorem. Let us see what this theorem says. The divergence theorem or Gauss theorem says that if T be a simple solid region bounded by a closed piecewise smooth surface, that means T is a simple solid region bounded by a closed piecewise smooth surface S, and N be the unit outer normal to S. So when a surface is given, something like that, one surface is given and its outer normal means like this. Its outer normal is also given as N, and if F equal to Pi plus Qj plus Rk is a vector field where P, Q, R have continuous partial derivatives on an open region containing T, then in double integral over S f dot ds equal to double integral over S f dot n ds, and now this is by Green's theorem. We can extend this, right? So that's equal to triple integral will come. Triple integral over T divergence of f dv. So inwards, the surface integral of the normal component of f, surface integral of normal component of s over a closed surface s is equal to the volume integral of the divergence of f over a solid T bounded by S. So let us see one example. We are asked to compute double integral over S f dot n ds given that f value. So we should identify here what is your p of x y z, right? So p of x y z is going to be as x plus sine z, right? Similarly q. What is q here? Q is 2y plus cos x, and last time is r, right? So r is given as 3z plus tan y. So this much is given. Now we know from the formula that double integral over S f dot ds is equal to triple integral over T divergence of f dv. So this is your f. Now we want to find the divergence, right? So that means del dot f. So del dot f is dou by dou x of p, dou by dou y of q, dou by dou z of r. You'll get this to be as 6. And the solid T is the unit ball B bounded by the unit sphere, right? Now this integral will become triple integral over B or R del dot f dv. But del dot f we have found to be as 6. So using this formula, divergence of f is 6. So 6 dv, right? So double integral over B 6 dv. But this B means it is a unit sphere. So we know what is the volume of that unit sphere. So in sphere, volume is 4 by 3 pi r cube. So in particular, when it's going to be r equal to 1 means it should be 4 by 3 pi into 1's cube, that is 4 pi by 3. So this is, we can substitute here. So remaining should be 8 pi. So the answer is 8 pi. So here we haven't bothered about the limit of this integration, triple integration and all, since we know what is the volume of that. If we don't know the volume of some solid is given, we have to put the limit also. We should draw the graph and put the limit for this triple integration. Okay, let us see another example. See here, we are forced to draw the graph. Okay, let T be a solid, bounded by the cylinder x square plus y square equal to 4. See, x square plus y square equal to 4, and the planes z equal to 0 to z equal to 3. So here z equal to 0 and here z equal to 3. So we should consider this cylinder. And let S be the surface of T. Calculate the outward flux of the vector field f of xyz equal to, see, it's given xy square I plus yz square j plus zx square k over s. Let us see how we can find it. So here the surface S is shown in figure 2. See, this is the orange colored one, right? This is going to be the surface. The flux of F over S is given by double integral over S F dot n ds, which by divergence theorem can also be found by evaluating triple integral over T del dot F dv. So as we have done in the previous case, first we want to find what is the divergence of F. So divergence of F means dou by dou x of P, dou by dou y of Q plus dou by dou z of R we want to find. So here when you are finding dou by dou x of x y square, you will get this to be as y square. Now here z square, here it should be x square. So what you are getting is y square plus z square plus x square. Therefore what you can substitute here, double integral over s f dot n ds is same as triple integral over T divergence of f dv, that's equal to triple integral over T x square plus y square plus z square dv. Now we want to add the limit for this. So the cylindrical coordinates when you are using, since it's a cylinder is given, to evaluate triple integral, we have, when you have it your cylindrical coordinates, your variable should be theta, phi and r. So here r, you can easily say that r in the direction of z. See here, r means in the direction of z. So r is varying from where to where? 0 to 3, right? Z is varying from 0 to 3 now. And next is theta. Theta means this entire angle. So theta is varying from 0 to 2 pi, right? Is it right? Next, what is coming? Oh, dr and theta. Since we are taking a cylindrical coordinate system, I made a mistake. So we are having cylindrical coordinate system, no need of phi. Phi is coming in the spherical coordinate system, right? So z is there, r is there, and theta, right? Now from where to where r is moving? So here whatever I given is not the direction of r. This is the variation for z. Now for r is varying from where to where? See, this is your r direction, right? So r is varying from 0 to 2. So 0 to 2. I repeat, since I made a mistake there, I repeat the process. For finding this triple integration, we are converting this into cylindrical coordinate system. Then in cylindrical coordinate system, we are having three variables as r, theta and z, right? Here z is varying from 0 to 3 and r is varying from 0 to 2 and your theta is varying from this entire angle, right? That means 0 to 2 pi. So our limit is given. So we have found out the limit now. So the integration is coming from 0 to 2 pi, 0 to 2, 0 to 3, r square plus z square. From where you got this one? By converting this everything into cylindrical coordinate system, right? R dz dr d theta. Now by integration, this will result integral 0 to 2 pi 30 d theta. So we'll get that to be as 60 pi. Okay, you should refer the cylindrical coordinate system there. Now example 3. Let T be a region bounded by a paraboloid cylinder z equal to 1 minus y square and the planes z equal to 0 to z equal to x equal to 0 and x plus z equal to 2, and let S be the surface of T if f of xyz equal to xy square I plus 1 by 2 y cube minus cos zj. Okay, f is given. Now we are asked to find double integral over s f dot n ds. So how the figure is coming? See here the figure. First of all, given that it's a region bounded by a parabolic cylinder. That means the cross section should be parabola. Okay, so parabolic cylinder z equal to 1 minus y square, and first we should draw the parabola 1 minus y square, and the planes z equal to 0. Z equal to 0 means xy plane, right? Then x equal to 0. X equal to 0 means y axis, right? And x plus z equal to 2. So we should draw that. So x plus z equal to 2 is this one, right? Now we will get a figure like this. From here we want to calculate double integral over s f dot n ds. So using our divergence theorem, it will reduces as divergence of f dv, and divergence of f we can easily calculate here. That's going to be 2y square. So substitute 2y square here. You will get the triple integral over t 2y square dv, right? So now we want to split into these three integrations and we want to put the limit also. So let us see how this is varying. First of all, we want to take the direction in the direction of x. So how x is varying? So x is varying from three coordinates. So x, y and z. So from where to where your x is varying? See, x is varying from this to here, right? That means x is varying from 0 to where? This curve, right? So 2 minus z. Am I right? No. X is varying from this is the curve, no? X 2 minus z means this surface 2 minus z, right? Now varying from 1 minus y square. Am I right? No, right? So 0 to x is varying. Let me draw it. So this is your x direction. So x is varying from this to this surface. Now this surface is x minus x plus z equal to 2. That means you are getting x is varying from 0 to 2 minus z. Now how y is varying? Y is varying from, you can take y's variation as from 0 to 1 also, and z is varying from where to where? Z is varying from here to here. What is the equation of this one? 1 minus y square, right? So 0 to 1 minus y square. Let us see how the limits. So x is varying from here y variation. Oh, here y is varying from this one. Okay, now from here, this here is one more minus 1 is I missed that one. So y is varying from minus 1 to 1. So this is the variation. So yeah, so here x is varying from 0 to 2 minus 8, z is varying from 0 to 1 minus y square, and dy, y is varying from minus 1 to 1. So this is equal to integral over minus 1 to 1, integral 0 to 1 minus y square, 2y square z, y square x, dz dy. Now upon integration, it will get 32 by 35. So only thing is that how to find the limit. Okay. Now this theorem can be extended to include regions that are finite union of simple solid regions. That is, if T be a region that lies between the closed surfaces S1 and S2. That means, see here, this is S1, this is S2. So closed region between those. Suppose something like this given, we can calculate this in the way T is S equal to S1 union S2. Now, if N1 and N2 denote the outward normals of S1 and S2, then the normal to S is given by N equal to minus N1 or on S1 and by N equal to N2 on S2. Now, applying the divergence theorem to T, see this is most important one, N equal to minus 1 on S1 and N equal to N2 on S2. Applying the divergence theorem to T, we obtain, see, 1 minus n will come, right? So divergence of f dot dv is equal to double integral over s f dot n ds equal to double integral over s1 f dot n ds plus integral over s2 f dot n ds, right? Now this will become, this here n will become minus n1. So like this. So double integral over s1 f dot minus n1 into ds plus integral over s2 f dot n2 ds. So this minus you can take it outside. So minus double integral over s1 f dot n1 ds plus double integral over s2 f dot n2 ds. Right? Now this is nothing but double integral over s1 f dot ds and this is f dot ds. So we can calculate it. Here is an example. Flux of an electric field. Consider the electric field E equal to Q by 4 pi epsilon naught R by R cube induced by a point charge Q placed at the origin of a three-dimensional coordinate system where R equal to xi plus yj plus zk. We are asked to find the flux of E across a smooth surface S that encloses the origin. So we want to find the flux of E across a smooth surface S that encloses the origin. So here the problem is that we cannot apply the divergence theorem since our given surface is not continuous at the origin. Now we want to avoid such a problem, right? So that's what we can do. So we can construct a sphere with a center at the origin and radius a that is small enough to ensure the sphere lies completely inside S. Right? So when you're having a small sphere inside of this, and we can say that the sphere is S1. If we denote this sphere by S1, then E satisfies the conditions of the divergence theorem for the solid T that lies between S1 and S. Now using our formula, what do you get? Using our formula, triple integral over T, divergence of E dv equal to minus, since S1 we have having two normals now, so one normal we should consider in the minus way or the negative side. So minus double integral over S1 E dot ds plus double integral over S E dot ds. Now divergence of V equal to 0. In example 4 we have already seen that 0, right? So refer section 15.2. So we have double integral over S E dot ds equal to double integral over S1 E dot ds, that's equal to double integral over S1 E dot n ds. Now to evaluate the integral on the right, note that the unit normal to the sphere S1 is r by norm r. So unit sphere, this one. Here normal should be r by norm r, since we are going to take the unit normal. Therefore E dot n is equal to, substitute for E and for n, r by mod r. Now that will reduce this as, here you will get mod r square, right? So mod r square by mod r raised to 4, you can cancel it. So at last you will get it as q by 4 pi epsilon naught into a square, because norm r equal to a on the sphere S1. Therefore what you're getting is double integral over S E dot ds equal to double integral over S1 E dot ds minus q by this factor into double integral over S ds, that's equal to right, that's equal to q by 4 pi epsilon naught a square into a of S1. Now what is S1? Sphere of radius, right? Sphere of radius a. So that will become q by constant into area, total surface area 4 pi into a square. So you can cancel a, whatever you're getting is q by epsilon naught. So this is the way we are going for surfaces like this. Here the problem was the divergence theorem we cannot apply directly, since E is not a continuous at the origin. Now here is a remark. The result in example 4 shows that the flux across any closed surface that contains the charge q is q by epsilon naught. That is, since any closed surface enclosing the charge q would trap the same number of field lines. Now, the principles of superposition you have studied in your physics class. The field induced by several electric charges is the vector sum of the field due to the individual charges, right? Now, it can be shown that for any closed surface, E dot nds double integral over S is equal to q by epsilon naught, where q is the total charge enclosed by S. Now this is called the Gauss law. Okay, this is called the Gauss law. Now we want to examine what is the interpretation of divergence. So for that, we should consider a sphere like this, representing the vector field F associated with the flow of fluid. Let P naught, Q naught, P naught, the Y naught, Z naught be a point in the fluid. Okay, so fluid is flowing like this. So we should consider a point here, P naught, that's X naught, Y naught, Z naught in the fluid, and let BR be a ball with radius R centered at P naught. So we should consider this sphere inside this, right? And having the sphere SR for its boundary as shown in figure. So as this figure, if R is small, then the continuity of divergence of F guarantees that divergence of F at P should be equal to divergence of F at P naught. So when you are taking divergence at a point P here and divergence at P naught, this both should be equal since your divergence is a continuous function. Therefore, using the divergence theorem, we can have F integral over SR F dot n ds equal to triple integral over BR divergence of F into dV. That's equal to triple integral over BR divergence of F at P naught. Both are same, right? P naught into dV. Now this can be written as divergence of F at P naught can be taken as a constant. So divergence of F at P naught triple integral over BR dV. Now dV divergence of F in at P naught into what's remaining is V of BR, volume of BR. Now volume of BR is a sphere with a center P naught and of radius R cube, right? So radius R. So its volume can be calculated as 4 by 3 pi R cube. 4 by 3 pi R cube. Now we can substitute it here and we can go for the approximation to improve. As R tends to 0, we have divergence of F at P naught equal to limit R tends to 0 1 by volume of BR into triple integral over BR F dot n ds. Now this equation tells us that we can interpret divergence of F at P naught as the rate of flow outward of the fluid per unit volume at P naught. I repeat, this says that divergence of F of P naught as the rate of flow outward of the fluid per unit volume at P naught. Hence the term divergence in general. That means if divergence of F of P is greater than 0, the net flow is outward near P and P is called a source. So whenever divergence of P is greater than 0 means from P it is flowing outside, right? Now in that case we will say that this P is a source. From where it is flowing? From the source, right? So that's why we are saying P to be as the source when divergence of P is greater than 0. Now if divergence of F of P is less than 0, then the net flow is inward near P. So when you're taking P, it should be inward like this. It should be. In that case, we will say that P is a sink. S-I-N-K. So whenever it's flowing from outside, we will say that P. That means divergence or is going to be F of P is greater than 0, we will say that this is source. When divergence of F of P is less than 0, we will say that P is a sink, called a sink. Finally, If the fluid is incompressible and there are no source or sinks present, then no fluid exists or enters BR, and accordingly what you are getting is divergence of f of p is equal to 0. So every point at p. So whenever your divergence of f of p is equal to 0, we can say that the liquid has been incompressible and it is not flowing anywhere, right? So this is the idea of your divergence and your divergence theorem also. So remember that divergence theorem is going to be the generalization of Green's theorem to vector fields. Okay, and remember how we have done some standard problems over here. Okay, so let me wind up here. Thank you for your patient listening. Thank you.